the recording. We could have some recorded here. And then let me do, I guess, two things. Number one, let me go back here and find chapter 29, number 25. Okay, I got that one. But in addition to that, let me get my phone all ready here. So I'll go share my phone and start connecting that. All right, that should connect up here in a second, and I'll even write down on the screen chapter 29, number 25, and I don't know how long this is, so I better put a page one. Let me change, I don't know which is better, to have it on the camera, the video. I think the video, because it zooms in just about the right depth. I don't have to do it myself. Okay. And then number 25. So a wire having a mass per unit length of 0.5 gram per centimeter carries a current of 2 amps horizontally to the south, where the direction and the magnitude of the minimum magnetic field needed to lift the wire vertically. Oh, let me read that again. I think I got it here. But so a wire is having a mass of 0.5 gram per centimeter. It carries a current of 2 amps horizontally to the south. And so maybe I'll just kind of, my picture here, draw a sphere kind of representing the Earth. And here is the north, and I'll call that the geographical North Pole and the geographical South Pole. And then they're saying there is a current. And so let me take kind of a wire here. And call it current I, because it says there is 2.00 amps of current horizontally to the south. What is the direction and the magnitude of the minimum magnetic field needed to lift the wire vertically upward? Okay, maybe I'll draw a second picture also. So here's north, here's south, and here's the horizon, if you will. So here is the current flowing 2 amps to the south. Now, maybe I'll start with direction. I know in the other discussions, we had some pretty good lengthy discussions about cross products. So I'll start there, because the point of this chapter is really twofold. It says, what if you have a moving charge in a magnetic field? There would be a force on it given by this equation. And an extension of that equation is, what if you had a current in a magnetic field? There would be a force given by this equation. And so that's the one I'm gonna focus on, okay? That's the one that gives me both the magnitude and the direction. And the reason we had a big conversation, and we can have that one again, it was a really good conversation about cross products, is because this cross product is giving us a way to calculate both its magnitude and its direction. And so the direction process uses a little process called a cross product using your right-hand rule. And this takes us back to Physics 121, where we did say, we had two cross products. One was torque is R cross F, and the other one was angular momentum which was R cross P. And cross products are not easy. Let me not worry about those, since those were last semester or 2 semesters ago, depending when you had 121. But what they said is a good way to figure out the direction is to take your right hand, you put your fingers in the direction of the first vector, you rotate your wrist until your palm is pointing in the direction of the second one. That's another way of saying your fingers can close. And then whatever direction is your thumb is the direction of your force. Now, for this problem, this is relevant here because if I look at, say, this picture, I want the force to be up. That's what is needed to lift the wire up. And it says here that the 2 vectors are L, and L is defined as a vector where the current is going. So in my picture, my first vector would be pointing from left to right. And so the question here is about the magnetic field. What would have to be the direction of this magnetic field? So in other words, my fingers have to point left to right. Which way is my palm pointing so that my thumb is up? All right, so if I held my hand like this, that would be wrong because my fingers are pointing opposite of that. So I'm going to have to kind of get my hand around the best I can. And so there's my fingers in the direction of L with my thumb upward. Let me turn my paper a little bit so I can do a little better. There we go. All right. So, I said that wrong. I want my thumb in my picture up. So let me put my hand flat. I got to turn a little more. Okay, right there. All right. So this picture, let me maybe put my hand right there. Okay, so my fingers are in the direction of L. My thumb is in the direction of F. So my palm, that is the direction my fingers would close if I closed them, is into my piece of paper. So usually the way we represent the magnetic field into a piece of paper is with X's. So I am going to put in my drawing then that if I had current going to the south and I had a magnetic field going from above my paper to below my paper, it would give me a force that is up. Now, maybe I need to remember what a compass rose looks like. So if here's north, here's south, and I turn it this way, then above the paper would be west, and this would be east. So looking at this, I would want a magnetic field that is going from the west to the east. So the direction is from the west to the east. Or at least a component going that way. The other component wouldn't matter, but the component going east to west. And now we could talk about magnitude, because that's what this cross product does. This cross product gives us a mathematical way of calculating. So I'll tear off that first page, but keep it handy here. And say, okay, let's look at page 2. And let me rewrite that formula. So the magnitude, or F vector, is IL across B. Now, using our knowledge of magnitude, this is the I, this is the L, this is the B, and then sine of the angle between L and B. And I can say it a little better now that I really want a field from west to east, because when the angle is 90 degrees between the currents and the field, you get your most force, because the sine of 90 is the biggest it ever gets. Or another way of saying the same thing, by arranging it so that the current and the field are 90 degrees, I can have the smallest field, because this factor, the sine factor, is the biggest. This would give me the smallest field that would levitate this. And that is really the question at hand here in number 25. It says, what is the direction and the magnitude of the minimum magnetic? So that's how I knew, even though I hadn't done the math yet, that's how I knew I wanted it to be 90 degrees to the current. Because again, 90 degrees to the current would produce the most force, which would allow me to have the minimum amount of field in order to levitate this. So that word minimum field was the key that allowed me to know that I needed it 90 degrees, which then if something is running north to south, west to east would be the direction of the field, would be 90 degrees. I get, obviously east to west would also be 90 degrees, but that would create a force that is downward, and that's not going to lift it up. So the magnetic field's got to be west to east. That's 90 degrees from the current, which is north to south. Okay, so now I can start to put in my numbers. I want to find this minimum field. The current, they said, is 2 amps. They didn't say what the length of the wire is. So I'm just going to put an L and hold off. I want to find the B, and I'll even put B minimum, because you get the minimum amount of field when the angle is at its maximum. This is maximized, so this will be minimum, so we can lift it. Now, the other side of the equation would be, well, how much magnetic force do we need? And I guess this takes us back to Physics 121. Maybe I'll just come over here and do a free body diagram. If you have a little object, if you're pulling up, call it F, but gravity is pulling it down, mg. So long as the force of gravity is more than the force you're picking it up with, the net force is down and the object goes down. It's not until the force you lift it up equals its weight or greater than its weight does it go up. So we would need a magnetic force that is at least equal to the weight of the wire. So that's why I'm going to then set that equal to the weight of the wire, mg. It doesn't have to be greater than mg. If it is, that's fine, but that wouldn't fit the definition of the minimum amount. So again, the minimum magnetic field is when we set it at 90 degrees and we have just enough to overcome its weight, not so much that we go shooting it up really fast. Now, if I bring the L to the other side of this equation and group it together with the M, I then have M over L. And M over L is the mass per length. So I don't know the mass of this wire or the length individually, and it turns out, fortunately, I don't really need to know that. So they say it's a 0.5 gram, and to do the units in kilograms, I'm going to do this. 0.5 gram and move the decimal 3. So 0.5 move it 3 is 0.0005 kilograms per meter. And so this would be a centimeter, 0.01 meters. So that is a 0.5 gram per centimeter, but written in kilograms and meters. And so this is 9.8 meters per second squared. This is the current. So this would be bringing it over and going 2 amps. And this would be the magnetic field. Maybe I'll just check the units. You might recall in the derivation of the magnetic field, we said the unit for a magnetic field is a Tesla, which is how much force you get on 1 coulomb of charge when it is moving at a speed of 1 meter per second. Oops, of course, newtons. So it's a newtons per coulomb per meter per second. So if you look at the units here, this right here is the newton. The amp we could replace with a coulomb per second. So there's the newton coulomb, and then there's the meter per second. And so that is a Tesla. Okay. So this is going to come out in units of Tesla. And I saw that coming. That's why it was important that I converted grams to kilograms and centimeters to meters. And now I can put in my calculator. And so this first term, 0.0005 over 0.01 for the mass density. I can multiply that by 9.8, and I can divide that by 2 amps. And we're talking about 0.245 Tesla.
Thank you. Yeah, I was confused about the mass per unit then, but yeah, makes sense.
Oh, yeah, that was a little tricky there because, yeah. They don't give you mass, they don't give you length, but they do give you group together.
Yeah.
In fact, I'll just kind of double check this, make sure I got it right. 0.245 Tesla, good. Oh, wait, eastward. What did I say? Yeah, from west to east, eastward. Okay, so the book and I agree. All right. Good.
Thank you.
My pleasure. All right, let me head back to the Zoom. Let me look at the chat room, see if any of you guys stuck anything in the chat room, or I'll just see whoever is brave enough to unmute their mic and jump in.
I got a question.
All right, go ahead.
Was that
Anthony?
Yeah, this is Anthony.
Okay.
I have another question before I ask about the actual chapter. I'm looking to get some fluid simulation software on my computer.
Oh, fluid simulation, huh?
Yeah. And I found some software that has a free student version.
Oh, good. That was the first thing I was going to say. I'm not real familiar with fluids, but this is a common free student stuff that fluids and fluid dynamics. You're depending on your major, you're probably going to have that fluid dynamics class. That's right about in your junior year. So it's like one of the first classes you take when you transfer. Some people take it right away. Sometimes people recommend that you transfer first because that cultural shock of going from a junior college or a community college to a university can sometimes be enough for you because, oh yeah, fluid dynamics is, well, fascinating, but really challenging.
Yeah. The only problem that I'm having is I have to input the school's information and my information. I think it's just to prove that I go to the school.
Yeah.
But I don't want to like mess up and they get an angry email from an administrator.
Oh, you won't.
Is there a way I can check to make sure that I'm not making any mistakes?
You'll be fine. If most of the checks I've seen is they require you to put in your email address.
Yeah.
And the computer checks it. It must end with an edu.
Mm-hmm.
If it doesn't end with an edu, then you don't qualify. You're not a student.
I think this one wants me to submit a picture of my student ID and then like the school and its address and its phone number or something.
Oh, a little more sophisticated, but and that's fine. They'll probably still send you a confirmation through your edu address, but you won't get in any troubles. No.
Okay.
Yeah.
Good.
No troubles. Nobody will care. Everyone will think one of two things. They'll think, oh, this is really a forward-thinking student. He's working ahead on his own, or this person is crazy. Well, they got too much time on their hands. Are they trying to kill themselves? Don't they have enough to do? We should give them more homework.
I'm trying to diversify my experience with computer programs.
Yeah, those are good things. But I would say you do have to be careful. There's a lot of really good things out there that will get in the way of your study time. You just get locked in.
I'm sure. Yeah, I've got an FPGA behind me that I'm doing now, and that I got to let go of that and do some other stuff.
Yeah, yeah. And sometimes I have students, they get so involved in clubs and activities, and they really let school get in the way of their education, and that's dangerous too.
Yeah. Mm-hmm.
It's a tough balance for everyone.
Certainly.
Mm-hmm.
Real quick, just while we're on this topic.
Yeah.
I had graphical analysis on my computer, but recently upgraded software on it otherwise, and now that's defunct. It doesn't work on my computer anymore. So I remember you had mentioned that there was a VR machine
Yes.
to access it, but I
Yes.
don't know how that is.
Oh, let's see if I can find it here real quick. I'll put it in the chat. But your school sent out, oh, I don't want to do that. That's going to end the meeting. Okay.
Sorry to interrupt, Anthony.
No, good. You're right.
I think I put it in this folder. Let me check. Here we go. Technical service for students. Okay. Yeah, this is it. Join our computer lab.
I went for the VMware, which is their desktop. I just put a link to SBCC's website. They have a whole way that you can go ahead, download the software, or log in remotely through a web browser. And it basically, you can pull up your student desktop from there. But this has like full extensive information as to how you set that up. So.
Yeah, if you sign in with, if you want to do it virtually and not download anything, if you sign in with your pipeline ID, then it lets you access that student desktop like Hunter was talking about.
Yes. Yes, thank you, Hunter. Yeah, that's exactly it. The virtual machine, and then exactly as they were saying, once you log in, you'll see the student desktop. If you ever logged in the lab in PS 117 or any of your computer classes, it looks exactly like that. And yeah, and I use it a lot when students send me a question about graphical analysis. I go, oh yeah, how do you do that? So I've got to log in and say, oh yeah, here's how you do a curve fit. And so okay. I got to admit, I haven't spent much time doing it, and that's a mistake on my part. That's actually a lesson I learned. I will tell you, because half of you took 121 with me, and the other half of you took 121 with Doug. And I use that graphical analysis heavily in 121, and so I never really explain it again in 122 and 123. I just say, oh yeah, you guys are familiar, log in, and maybe you forgot a little bit. I'll come around to walk around the lab and help you. And I realized after I had said that kind of this semester that wait a minute, I don't think at least half of you used graphical analysis in Doug's class. So anyways, so I note to me, next semester, at the beginning of the semester, instead of just throwing you guys to the wolves, I'm going to say, okay, here's how you get on the virtual machine, and here's how you use graphical analysis.
Okay, thanks.
But yeah, go to that and log in, and it's just like your pipeline account. And then right on your desktop, you'll see a bunch of software you could use. And graphical analysis is one of them. You probably aren't interested in like Microsoft Word, but some students don't have the funds to buy it. It sounds like you have your own word processor. Although Google Docs is free too, so I think a lot of students use Google Docs.
Yeah, I found the graphical analysis trend lines and formulas have been a bit better at doing that for graphs and stuff.
Yeah, and you guys heard me say in the lab, I keep saying that, because I think graphical analysis is just so user-friendly, and that's why we've used it for years and years. Even though things like Excel and Google Sheets are more powerful, they're not as user-friendly at the beginning. So I've just always said, we've got so much tough physics to learn, just use graphical analysis, and someday it would be good for you to learn either Excel or Google Sheets or both. And once you learn one, you know the other really. But the right now, just learning to do a graph and do a curve fit will keep your brain power free to focus on physics.
Mhm.
All right, so thank you, Zach, for that. Okay, so let's go back to
Real
Anything?
quick, I was wondering, is it scheduled in that we're gonna have like a kind of off week before the exam like we did last time?
oh shoot, wait, did I hit the record?
Yeah,
Yeah.
it's recording.
Yeah, you
Oh,
did.
I did. Okay, good. All right. I'm sorry, Hunter. That just dawned on me while you're talking. What?
Oh no, I was just saying, are we gonna have like another like scheduled like catch up week that we kind of have before the exam like last time or no?
Oh, I think so. I don't want to say yes or no to that. I need a. I think so.
Okay, cool. Thank you. That was all.
I need a look ahead.
Wait, what did Hunter just ask? My audio kind of cut out really fast.
Well, for the last test, we took the test on a Thursday or no Tuesday,
Tuesday.
and the week before that was really no new material.
Yeah.
Okay.
And we will have either a half a week or a full week. I'm not sure on the schedule. So it could be where we get into that week and there's no new material, but your test is on Thursday, or it could be no new material and then it's the next Thursday. But I'm kind of thinking the former. I think we'll start the week and I'll say no new material for the week, but yet your test is on Thursday. So I think this time we have a half week. That's kind of what my memory reminds me. Yeah. So,
Thank you.
November 3rd, right?
I do remember. Yeah, I'm going to go to the calendar then. I have many times kept typing in November 3rd, November 3rd, November 3rd, because that definitely is the test. Let me call up your syllabus here. And it looks like, so we are in week 8. And so we've done 27, 28. We're doing 29. Next week we will do 30. Yeah, it is the same. So the week after that, we will have catch up / start 31 if you want to. It's not on the test. And that was kind of how I did 27. Yeah, it's exactly the same. And then the next week we have the test and chapter 31. So if you've done anything the week before, you won't have as much work after you take the test. But if you need the time to catch up and get ready for the test, yeah, you have a whole catch-up week on week 10. Yeah.
Cool. Thank you very much.
Yeah.
Cool. Thanks.
Yeah. So a little flexibility in there. Mm-hmm. Nice. Okay, finally, Anthony. Yes, I'll come back to you.
So, there's no chapter 30 homework on the PDF that you sent, but there is chapter 30 homework on the syllabus. So should we just look in the book to find those?
You can just look in the book. I thank you for telling me. I would feel better if I also sent it to you with an apology to everyone. Let me just check that. So here's 29.
Yeah, I actually just checked that. It does that way. That's very strange.
And then, yeah, it totally skips 30. Okay, well, note to me, because let's see, today's Friday. On Sunday, I'll start putting together your week assignment, and that will be it. It'll be chapter 30, and I'll make a PDF at a chapter 30. So my apologies. This was, yeah. I should have just proofread it a little better. I made these and I just literally cut and copied them. This was like last year, and then we put them in the copy machine, and apparently when it form feed through there, a bunch of pages got stuck together. Because every once in a while there's a page missing. So I probably, and actually now that I should even do it better. Last time I just literally just cut them out, but now that I have my little snippet and my PDF of the book, I should actually just digitally copy problem by problem and make my own PDF that would be in color coded. It would be better. Yeah. So note to me, that'll be my goal for next year. So you guys will be gone.
Yeah, update all
Bigger and
that.
better things by then, but the PDF. But as you said, you can see all these in the textbook. So you can just read the number on the syllabus and open the PDF in the textbook, and you'll be fine. I suppose now. See, I made all this as a side note. I made all this years ago before we did the PDF of the textbook. But now I could just as easily forget the PDF but students have told me they've liked it. They like the homework just in one spot. You know, it's
It's
you don't have to open the book or anything. So I'll probably still keep it, and then students can have that option. It just needs to be a better copy, not miss some pages.
right. So, did you want to look at chapter 29, number 27?
Yes. So chapter 29, number 27, page 1, number 27, chapter 29, timestamp here at about 3:42, and I'm going to get up here and shut the blinds in my window. The sun's starting to come in on me. It's getting warm. Warm day today. In fact, what I do with my water, give me another second. I'm going to grab my water. All right. Get a little water in me. Okay, so let's get started with this one. Now I'll scroll up here. So number 27. 27. Where is 27? Here we go. So a wire of 2.8 meters in length carries a current of 5 amps in a region where the magnetic field has a magnitude of 0.390 Tesla. Calculate the magnitude of the magnetic force on the wire, assuming the angles between the magnetic field and the current are. And they list 3 different angles. All right. So as I think I was showing in the last problem, and I probably even joked about it in the videos. Haven't really joked with you guys on here, but would you like to know the answer to all the homework problems in the chapter?
Is it F equals QV cross B?
Yeah, that's it. And then, of course, if you put a bunch of charges together, you get a current. So the extension of that equation is this one. And that's the one I'm going to focus on here in this problem.
So here's the question that I had.
Yeah.
The L cross B,
Yeah.
does that become LB sine theta
Yeah.
after the cross product? Okay.
Yeah. And so when it comes to calculating magnitude, we just take the magnitude of L, magnitude of B, and the sine of the angle between them. So in this case, the current, I think I read 5 amps, did I not? 5 amps. A length of 2.8 meters. A magnetic field of 0.390 Teslas. And then the sine of, and then we would have either a 60 degrees or a 90 degrees or 120 degrees. By the way, the sine function is symmetric around 90 degrees, so those are the same.
Mm-hmm.
Now, if you did a right-hand rule, they would make a force in a different direction here. But well, depends. I shouldn't say it depends. Okay. So I'll calculate the number, but I think actually kind of helpful, and this one could actually be the unit. You remember a Tesla is a Newton on a Coulomb moving at a meter per second. And then of course we have the meter from the length of the wire, and an amp is a Coulomb per second. So that meter cancels off, that Coulomb cancels off, that second cancels off, and you have a force of Newtons. And now it's just a matter of plugging this in. So 5 times 2.8 times 0.39, and I'll just put this as 5.46 newtons, and then I'll leave sign of, and then it's either 60 degrees, 90 degrees, or 120 degrees for each of the 3 options that they have us there. And of course, 90 degrees, sine of 90 is just 1.
Mhm.
So I'll put B as 5.46 newtons. And C or D should be the same thing. So times sine of 60 degrees is 4.73, 4.73. And let me just check. I don't think they asked for any kind of direction. They didn't give any pictures or anything.
So, last part of the question is not this question, but there's also the equation F equals QVB sine theta.
Oh, yeah, this one here?
For
Yeah.
a single particle
Yeah.
versus the current.
Yeah, well, good way of saying it.
Okay.
And I would even say that, this one here is really a group of particles. So they're kind of the same equation, and you've grouped all your moving charges together and called it a current. That's how this equation became this equation. So there's really only one equation here. However, I must say that you should learn both of them so that if you saw a problem where it was a single charge moving, like some of the ones we did in the earlier sessions today, I would use the Q, like we had that positron in there. And it's a single particle, so I would use this one. But the one you just asked about was a whole set of charges moving called a current, and so I used that one.
Right. Okay.
Yeah.
Thank you.
Good. All right, let me jump back to the chat room, see if anybody's thrown anything into the chat. Looks like Daniel says, wait a minute, on the lab. Oh.
Yeah, I had a question.
Yeah, I don't want to skip over you.
So you did let's see, the calculation for the resistivity of copper. Which one do you want us to use? Should we use the one that's closest? Should we take the average of what we got through the resistivity A through D and then compare that? Or, I mean.
Yeah, why don't you do this? Just to finish it up, the exact what you do is not too important. I'm glad I get the impression you got the idea about the resistivity, but
yeah,
the first 4 coils are all copper.
Yeah.
So whatever resistivity you got for those 4, average those 4, and
Gotcha.
then see how close you get to the accepted value.
Okay, cool. And then I think the other one was, for 2, I guess, because you just went really, really quick, which I guess maybe it's completely obvious, but is it just the temperature must remain constant for a resistor to obey Ohm's law? It asks what conditions must be satisfied for a resistor to obey Ohm's law.
Yeah.
But then it does say conditions plural, so that's why I was like, well.
Oh. Yeah, but the end result of a lot of conditions, so that's why they have it plural, is that the resistance does not change when you turn either up or down the voltage.
Okay.
And what I was trying to say in there, and I don't think it's a very good question. You might call this the hard and soft form of Ohm's law, because when Ohm's first presented it, he said if the resistance does not change as you adjust the voltage, then you get this straight line, and that's called Ohm's law.
Mm-hmm.
Later on, it was discovered that everything changes its resistance with temperature at least a little bit. So today we kind of say that if you're working with a resistor, and maybe, you know, when you turn something on like a computer,
Mm-hmm.
it starts at room temperature, and then when you turn it on, the internal electronics get pretty hot. I mean, not hot enough to boil water, but they get pretty hot. And the resistors in there are designed to stay pretty constant. Perfectly, no. So there really is no such thing that follows Ohm's law exactly, but they're pretty close within the range that we use them. So that's kind of the answer we like to give, that if the resistance does not change when the voltage is adjusted, and then we don't say it, but we kind of mean, and I'll put in air quotes, within the range that we're working with, then we say it obeys Ohm's law. So
Okay.
that was a long way of saying, just give the short answer by saying, if the resistance doesn't change as you adjust the voltage, then it obeys Ohm's law.
Okay, cool. Thank you.
And I think you saw in that experiment, I had 2 resistors and a light bulb, which I'll count as the third resistor. And the first 2, even though I turned up the voltage to 5 volts, and they got pretty warm. I mean, you wouldn't, if you were in the lab, you would have noticed it. And you might even saw me, because I remember unhooking that blue resistor, and it kind of burned me a little bit. I grabbed it, and dropped it real quick, because it was hot. And they get pretty hot, but yet their resistance didn't really change much. I saw a straight line in that data. And of course, the one that changed a lot, which is tungsten, is what's in that filament of that light bulb. And so you saw that change by an enormous amount. I think, I'm trying to remember the slope we got. When it was hot, it was a much steeper slope, something like 4 or 5 times steeper than when it was cold.
Cool.
So, yeah, don't make a big to do over whether it's Ohm's law or not. But that's technically Ohm's law, that the resistance stays constant even as you change the voltage, which means you're warming it up. If you're turning the voltage up, if you're giving it more current and it's getting more heat. But if you measured it really, really, really careful, or you turned it up really, really hot, you would see that the resistance does change. But from 0 to 5 volts, even though it gets pretty warm, it's just warm to the touch. It's not real hot. So. All right, so those are the good ones. Let's see. That was number 27, right? Okay, so looks like Daniel, you're next here in this. Could you do number 8 and explain y for the x-axis is any x when you get a chance? Oh, when I get a chance to do it. Okay, all right. Is any x. I better read that because I don't completely understand your concern about x here, but I think I will once I read it. Okay, so I'll make a little note here. Chapter 29, number 8 at timestamp 3:55. And I'll come over here and scroll up here to number 8. Oops, that's the wrong class. Try that again. Number 8. When an electron is in a uniform electric and a magnetic field, and it has a velocity of 1.2 times 10 to the 4th meters per second in the positive x direction, and an acceleration of 2.00 times 10 to the 12 meters per second in the positive z direction. If the electric field has a magnitude of 20 newtons per coulomb in the positive z direction, what can you determine about the magnetic field in the region, and what can you not determine? Great question. Yeah, I can see why it's still number 8. All right, so let me begin by kind of making a little, to the best of my ability, a 3-dimensional grid. And so here's the x-axis, here's the y-axis, and coming out of the paper is the z-axis. Now, the first part of this says it's an electron, so okay. That right there makes me think that I'm going to be dealing with a force on a charge moving in a magnetic field, especially given the material. But as I read on, it says electron is in a uniform electric and a magnetic. So I need to go all the way back to chapter 23 and probably look at this equation also. Because if I have both fields, there would be a force from each of those fields, a force from the electrical field and the force from a magnetic field. Right, so again, just reading it, an electron in a uniform electric and magnetic field has a velocity in the x direction. All right, so it's moving this way. And of course, the magnetic field, excuse me, the magnetic force is related to that velocity and the magnetic field. And so that the direction and the magnitude of that number is crucial. In fact, maybe I'll just write it in here that this velocity is 1.2 times 10 to the 4th meters per second. Now, here's a big thing right there where it says the acceleration is in the z direction. So I'll put a little arrow in the z direction. It looks like it comes out to be 2 times 10 to the 12th meters per second squared. And I'm going to jump back to Physics 121 for a second. And I know this, that the net force is equal to mass times acceleration. All right. So maybe I should put a sub B under here and a sub E under here, because if I take what I've learned last semester, or maybe I should say Physics 121, that may or may not be the last semester for you. But this net force then is a combination of the magnetic field and the electric field. So these two add together to give me the net force. And again, the net force is its mass times acceleration. So if I focus for a moment my attention just on direction, with the acceleration being in the z direction, that would tell me these two forces have to add up to give me a z direction only. In fact, I think I'm going to even calculate what is the net force, because I know the mass of the electron is 9.11 times 10 to the negative 31 kilograms. And the acceleration is this 2 times 10 to the 12th meters per second squared. And so grabbing this calculator and saying 9.11 times 10 to the negative 31, and multiplying it by 2 times 10 to the 12th, I get a 1.82 times 10 to the negative 18 newtons. Okay. So again, what last semester or Physics 121 tells me is that these two forces, the magnetic and the electric, when they add up together, they have to be in the z direction. So I'll put a little k hat there. And they have to add up to this amount. Now, as I come back and read this a little carefully, they say this: if the electric field has a magnitude of 20 and in the positive z direction, right? So they are indirectly giving me this part of the puzzle. They are telling me what is the force from the electric field. It would be the charge, which is a negative 1.602 times 10 to the minus 19 coulombs. That's the charge of the electron. And they're saying the field is 20 newtons per coulomb in the k hat direction. Okay, now if I just calculate this, 1.602 times 10 to the negative 19, and I multiply it by a 20, the magnitude comes out to be 3.20 times 10 to the minus 18 newtons, but its direction is in the negative k hat direction. Now, why is that important? Well, I'll say it again. The two forces, the magnetic and the electric, must add up together to give me a force in the positive z direction. The electrical force by itself is in the negative z direction. So if I were to maybe put the electrical force in my diagram, I would point it back in that direction. That tells me right away that the magnetic force must be in the positive z direction, because the only way I can add those two together and get a result in the positive z direction is that the magnetic force has to be enough to overcome the electrical force in the negative direction and be a little bit bigger than that, so it comes out to be in the positive z. And so I know that the magnetic force is all in the z direction. If this magnetic force had like an x component or a y component, then the net force would have to have an x or a y component. And I don't have that. Okay, so I'll say it again. There's two forces, magnetic and electric, that add up and give me the net. And since I know the net force is in the positive z direction, and I know one of them, the electrical, is in the negative z direction, the other one right here must be in the positive z direction. In fact, I'll just continue with this math on the next page. And because
there's both a positive and negative in the z direction, do they cancel each other out?
Well, apparently they don't cancel completely out, because I have to end up with a net in the positive. So this would tell me that the magnitude of the magnetic field is not only in the positive z direction, but it is greater than 3.2, because 3.2 would exactly cancel it off. It's got to be 3.2 plus 1.8, which is about a 5.02. And that's the math I was about to do. Here's what I'm trying to say here is the net force which is equal to the electrical force plus the magnetic force, would look like this. The net force is that 1.82 times 10 to the negative 18 newtons in the k-hat direction. And the electrical force we just did was a negative 3.20 times 10 to the negative 18 newtons, k-hat direction. And so this will allow me to figure out what is the magnetic force. I'll move this to the other side so it becomes a plus. And so a 3 plus a 1 is a 4, and an 8 and a 2 carry, so that's going to be a 5, 0, 2 times 10 to the negative 18 newtons in the k direction. So coming back to my picture, this is 5.02 times 10 to the negative 18. So it's in the positive z direction, but it is bigger than the electrical force by quite a bit. So that not only does it cancel off the electrical force, there is a net force in the positive z direction. So the magnetic force is quite a bit more. So you're going to put them side by side. The magnetic force is 5 times 10 to the minus 18. The electrical force is negative 3.2.
Okay.
All right. So let me get back to the question. It says, what can you determine about the magnetic field in this region, and what can you not determine? Okay. So it's centered around this cross product again. And so we know that the force, magnetic, is the Q, that's the electron, times its velocity, crossed with its magnetic field. The meaning behind this, and I think you were here when we got into a long discussion about it going in a helix pattern. If you, can I say, this math says that the force is perpendicular to both the velocity and the magnetic field. All right, so coming back to this picture, since the force has to be in the z direction, maybe I'll find a new color here. The magnetic field must have at least some component that is perpendicular to the v, but also perpendicular to the z. Now, it doesn't mean all of it is that way, but I'll draw a line. I don't want to put an arrowhead on it quite yet, but I'll call that the perpendicular component of the field. There can also be a field that is in the direction of the velocity. Because again, studying the math here on a cross product, the cross product says that you want to look at, say, the velocity, and then how much of the field is perpendicular to that, getting you a resulting perpendicular direction. So the part that contributes to the strength of the field would be the part that would be the magnetic field that is in the y direction. The part of the magnetic field, if there is even a part that is in the x direction, according to this cross product, would give you no force. And so the part of the question that says, what is it we can't determine, is we cannot determine how much of the magnetic field, and I'll call it B parallel, how much of the magnetic field is in the x direction. You could have a little, you could have a lot. It doesn't matter. It doesn't have a force on this electron. We have no way by this experiment to determine if there's a little or a lot of the magnetic field in the x direction. That's impossible.
So that's why it can be, that's why it may be any point at in the x direction.
Yeah.
Okay.
Oh, yeah. And your question said something about the x direction.
Yeah. And I did the math for the y direction.
Oh, good.
But the answer for 29.8 says that the z direction is 0. Why is that?
Oh, okay. Okay. I like your question. Let me hold off here. Let me just do a calculation for the y direction, because I can write this cross product as v times how much of the field is in the y direction. And so the velocity was what, 1.2 times 10 to the 4th, and then this is the y direction. So getting the y direction, 5.02 times 10 to the negative 18 divided by 1.602 times 10 to the negative 19. That answer divided by 1.2 times 10 to the 4th. And so this would be 0.0026 Tesla in the y direction. So I'll get to your z direction, but what I hopefully got out of this is the field in the x direction is completely unknown. There's no way from the information we know we're going to do that. The field in the y direction must be 0.0026. And then the last part of this, the z direction, is got to also be 0. Why? Well, come back to this picture. If it had a field in the z direction, that means that z direction would be perpendicular to the velocity, and there would be a force. And if you put your right hand out here, that force would be a force in the either the positive y or the negative y. But we know from the information there is no force in the y direction.
Okay.
So the only way we can have no force in the y direction.
You mean z direction? You were pointing at the k but saying y.
Yeah, okay, wait. But I'm talking about force, not field.
Oh, okay, I see.
Okay, so let me say it again. So we know from their definition of, not definition, but the information that was given us about the acceleration was all z.
Hmm.
From that, I conclude that the net force is also all z. Okay, this is the force.
Okay, that makes, okay. Yeah.
There is no j hat here.
Okay. Yeah.
Now, if we come back over to here, if there was a field, a component of the field in the z direction, with the electron moving in the x direction, it would create a force in the y direction. See, and we have no force in the y direction. And so that tells me we must not have a field in the z direction. So a field in the z direction, when it's moving in the x direction, would produce a force in the y direction And we don't have that. So that makes me come to the conclusion that there would be no component in the z direction.
Okay, that helps a lot.
Yeah. And now that I'm going to flip over to the answer sheet. Yeah, they say may have any amount in the x direction. Agreed. It has nothing in the z direction. Agreed. And in the y, we calculated the same amount. They wrote it as 2.6 milliteslas. But what I didn't do is I didn't say what direction it would be. And let me fix that. I just said it would have this magnitude because I was calculating the magnitude of the force, which give me the magnitude of the field. And so let me do a little better and come over here. I need the right-hand rule for this. That's why earlier I said I didn't want to put an arrowhead on this. Now let me put an arrowhead on it. And so to do a cross product, I would put my fingers in the direction of the velocity and my palm in this direction so that my thumb would go, and here's where you got to be careful. I don't actually want my thumb to go in the positive z direction. I want my thumb to go in the negative z direction because I want v cross b to be a negative k hat so that when I multiply it by a negative charge of an electron, it's going to get a force in the positive.
Okay, so that's why it's negative y direction, because if you want the z in the negative, then your palm is facing downward.
Let's see. So, yeah, to get inward, I want my palm facing downward. And so I want my y component to be down. So now I'll put an arrowhead on this so that v cross b, that alone gives me a negative k hat. That's this part. Then when you multiply it by the negative of the electron, the two negatives cancel, and you end up with a force that's in the positive direction. Kind of another way of saying the same thing is v cross b is the direction a positive would be pushed, and a negative is going to be the opposite of that. So since this is an electron that is being pushed in the positive z direction, I want my v cross b to be in the negative z direction, which is going to make then the field in the y direction to be down, which then finishing this off would say b in the y direction should be a negative 2.6 milliteslas.
Okay, cool. Yeah, that explains.
And of course, likewise, I can't put an arrowhead on the x component. It wouldn't matter which way the x component was for the magnetic field. So the x component is not doing anything. It's wasted. So obviously, if you're really trying to engineer something, you would design it without a x component because that's wasted effort.
Awesome, thank you.
Ah, nice. That was a good one. All right, let me jump back here to the Zoom chat here. That was, let's see, number 8. That was Daniel. Could you please do blah, blah. Oh, all right. Well, I don't see another one in the chat room. Does that mean you guys are just hanging out and absorbing the good vibes? And maybe kind of prepping you for your chance when you get a time to do it?
Hopefully. Yeah. All right. Thank you, Dr. Young. I'll see you next week.
Okay, my pleasure, and good luck to you.
Thank you.
Thank you so much. And a smiley face. Yeah. Take care. Yeah, you too.
What's because the test is like 2 weeks away. So what would be a good way to start prepping for it?
It's two. I guess you would know here. I wanted to say it's on the 3rd.
Yeah, it is.
Yeah.
Yeah. Well, that's really 2.5 weeks. Okay. So next Tuesday, then it'll be 2 weeks. So it's 2 weeks and 4 days. So let's not rush it too much. But first of all, my answer would be this: that make sure that you are completing chapter 29 this week. So you're not behind. Because as Hunter pointed out, and I'm glad he pointed it out, so I could start helping students with that. You're going to have the whole week of, let's see, Monday the 26th through Friday the 30th. And of course, I'm not even counting the weekend, and you guys know your students, and so weekends are part of your work schedule. But you're going to have that whole week from Sunday the 25th to Saturday the 31st, Halloween, to kind of catch up on anything you're behind. And so my best recommendation would be don't be behind. Use that week to really study hard for it. The best thing you could do right now is to not get behind. And if you don't completely understand it, that's fine. You've got that whole week to help digest it. That's really my thoughts. And I will even throw this at you too, especially for the rest of you here in this the Zoom here, that this next chapter coming up is the hardest of the 4. Okay, so all the more reason why don't be behind. If you can really work on these, and it looks like you guys are. You guys, I'll take my phone cut out again, but maybe just as well. But you guys are about to hit a really hard chapter again. Now it's not as hard as some of the ones you've done already, so don't over panic. But it is very three-dimensional. It's got some tough integrals. We're basically going to do the same thing for magnetism that we did for electricity, where we did Gauss's law. It's going to be called Ampere's law. It's really kind of the same thing. Also, instead of Coulomb's law, we have Biot-Savart law. And maybe what makes it hard is your author, he puts both of those
In one chapter.
He says, you guys are good at this now. We spread it out over 2 chapters at the beginning of the semester. So now it's really the same thing. You guys are proficient at that. And that's kind of true. But magnetism, because of its 3-dimensional visualization, is a little bit harder. So you've got all those tough integrals, plus you have the 3-dimensional visualization of it. Like I said, but on the good side, you have that experience that you already did. So.
Okay. So like this we can get caught up on homeworks, and then.
Yeah, all the more. The best thing I think you can do at this point is not so much review for the test, but to make sure you've got everything done so that you can start the next chapter. In fact, I would even say if you by some magic got all the homework done on Saturday, don't even wait until I send it out Sunday night. It's the next chapter. To read it first, you know it's the next lecture in the series. So wherever I left you off, I want to say it was lecture 17, but I can't remember. But you got the playlist. Just go to the next one.
Okay.
Yeah.
Cool. Thank you.
Now that I look at it and think about it, I'm glad if we pound that out next week and we have that whole week to really be a review week. And for anybody who's completely on task, they can get started with the next chapter. But
Is that kind of is this kind of how the third test is going to go too? Like we're going to have 4 weeks filled with new material, and then the 5th week, like prep for the third test too? And then,
yeah, that's how I do the first 2 ones. But sadly, I think we kind of run out of time on the third one. I think there's only 4 weeks or something, and so we don't have the prep week.
Is it just like instead of having that full prep week, is it on like the Thursday of that prep week?
Yeah.
And then it's just the final after that?
Yeah. Yeah,
The
like I guess
semester
I could
feels like it went by really fast.
count it. 1, 2,
already
3, 4.
like-
Yeah.
More than halfway over.
And it's also why you'll see as we get to the end, chapter 34, we kind of shortchange it a little bit. It's got things that are both straightforward and really complex. And so we kind of just do the straightforward, kind of mention the complex and say, that's just kind of where we'll have to call it a wrap for the semester. So yeah. I mean, it looked at that way. It looks like we're getting towards the end, but we got a long way to go to the end. So
Yeah.
I think there are 15 weeks, and so 7.5 would have been this last Wednesday. So we're really halfway. But we're working towards the third test, which is the 2/3 mark. Yeah.
The first 2 chapters in this section for the next test, I mean, they're kind of pretty circuit driven. I mean, at least that's what I'm kind of getting from it. Would you say?
Did you say it was circuits?
Yeah.
Yeah.
Like there's a lot of problems with circuits, and therefore, and I know capacitors and stuff were on the last test, but would a lot of that factor into problems for the test for these ones, even though they're not really focusing on capacitors?
Yeah, one thing I suppose kind of good about this second test is it's clearly divided into 2 groups. Chapter 27 and 28 are about circuits, and 29 and 30 are magnetic fields. Now, they do overlap a little bit because as you are about to see into the next chapter, magnetic fields are created from currents. So a kind of overarching problem would be, say, here's 2 batteries, 3 resistors hooked up in a circuit. What is the magnetic field from them? So you have to do your circuit first to figure out how much current there is. So that's like a chapter 28 problem. Then once you got your current, you could use that to find the strength of the magnetic field. And that's what we're going to do in chapter 31. Now, let me also backtrack to your question or your comment about capacitors. It's true that we were introduced to capacitors during the last test, and it's true that they were on the last test. But what we did not do is we did not have capacitors and resistors. We did not have RC circuits in the last test. So that's the kind of thing that you did homework on, you did problems in chapter 28 on, and I would be, saying you be ready for them on the test, the RC circuits. So there wouldn't be a circuit that is just all capacitors. In fact, any circuit that's all capacitors is kind of boring. It's not practical. All of our usefulness with capacitors come together when we hook them with resistors and batteries. And now we start having usefulness to our capacitors. As I said, one of them is just storing energy. Another one is a timing device, and because it's an RC circuit, it has a certain timing you can do. I think you also saw it as a filter. Works great as a filter. It also works great as a sensor. Anytime anything vibrates or bumps and the distance between the plates change, the capacitance changes, that changes the time constant. And so they make great sensors. We can detect earthquake with them. I don't know if I got a chance to mention in the video lectures, but I think one of the best modern places of the capacitor as a sensor is the touch screen on your iPhone, or your phone, your smartphone. And you touch that and you change the capacitance, and that changes some charges. And so that's how our whole touch screen devices work these days. The original ones were a little different. They were change the resistance when you touched them. I even have a lamp. It's kind of an old lamp, so it's been around for a long time, but the capacitance is hooked to the metal casing on the outside. So when you just touch the outside, it senses it and the light goes on. There's not an on and off switch. It's just touch the outside casing.
We have a lamp like that too.
Yeah. So somewhere they use the casing on the outside, and so the human body probably has about the same capacitance as the housing on a lamp. So you can change the capacitance by a lot, and the little sensories inside. So that's another great place for capacitors. But obviously, we don't really get that far in this class. This is not a circuits class. This is a class to kind of get the fundamental physics of how the circuits work, and you would do more of that in a circuits class. And so some of you will be doing that because you're going into electrical engineering and designing. Others of you maybe are more mechanical. So I don't know if you take a circuits or not. Sometimes they require one semester just because it's good to have a background in it. So.
All right. So maybe just might be a good idea, in addition to just really hitting hard the RC circuits, Kirchhoff's law, and all that, may take a glance back at the capacitors chapter and how they
and Daniel, the same thing for you too, that you asked about what to study, and I said really the best thing is really not so much to study yet, but to make sure you're on top of everything. But if you get a little bored, and I can see how you could get burned out and say, well, I'm not really done with it, but I don't have the strength to go on, but I don't want to lose time. You can go back and review the circuit stuff, because there isn't going to be any new circuit stuff between now and test day. All the circuit stuff you've learned between now and test day, you've been exposed to. So, you can go back and say, hey, I'm going to try a tough Kirchhoff's law. And you can just open up chapter 28 and put your finger on one and go, I'm going to try that one right there. Maybe it's all resistors. Maybe it's resistors and capacitors. Who knows? But that would be a good review, and just take you a break from trying to learn all the magnetism, and yet still give you a chance to start reviewing, so that when the review week comes, you've already done the circuits review, and now you want to just do the magnetism review.
Cool.
All right, well, I'm going to head out. Thanks so much.
Oh,
Yeah.
okay. Oh, yeah. So, all right. It's our 4:30. So good work with all you guys, and we'll head on out too, and wait for any questions you might have, either by email or video solutions, or next Friday.
Yeah.
Good.
Good
See you then.
weekend.
All right. Thank you very much.
Bye.
Thanks. Bye.